All right. Welcome in today. We're going to talk about a couple of final things in chapter 23 today to wrap it up. But last time we met, we were talking about Ohm's law, right? Current is equal to voltage or electric potential over resistance. Okay, and the first thing we're going to talk about today is kind of the next step from that, and that's electric power. So electric power is kind of has more to do with the energy, right? Because here's the thing: is that as an electron moves through a circuit, or as the energy of that electron moves through a circuit, it creates heat, right? Because there's friction; it's running into other atoms and molecules, unless it's in a superconductor in which everything else is standing still. But it's going to expend energy. It's going to use up some of its energy in the travel, right? Now, this energy may also be used to heat something, right, or to turn a motor or to light a light bulb, right? But at any rate, uh, energy is being used, and the rate at which that energy is used is electric power. Okay, so the rate at which energy is used. Okay, now power is equal to the current times the voltage. Okay, power is equal to the current times the voltage. Okay, now the units for power are watts. Okay, and of course named after another gentleman with the last name of Watt. But if you want to break that down even farther, we could say those are amps and volts, right? So a watt is an amp and a volt. Okay, so for example, let's just use an everyday appliance or everyday thing that you know, a 60-watt light bulb then, right? If it's in a house that has 120 volts, right? How much current does a 60-watt light bulb use? Well, if we solved for I there, we would say I is equal to 0.5 amps. Okay, so just keep that in mind. A 60-watt light bulb only uses about a half of an amp. Okay, a 100-watt light bulb in a regular 120 volt house would be, if we divide that out, 0.8 amps. Okay, so again, not a ton of current necessary to light a light bulb. Okay, and we're going to talk about different types of light bulbs here in a little bit. But this is how power is measured, is in watts. Now, really, there's a difference between power and energy. When the electric company sends you energy, because that's what they're sending you, energy is measured in electrical terms as power over a given time. Not over time like as in a fraction, but like for how long that power is given, right? And we would measure that in, usually it's measured in kilowatt hours. Okay, if you look at your parents' electric bill, it's going to tell you how many kilowatt hours were used. Okay, so a kilowatt hour is how much, is a kilowatt per hour. It's the amount of energy transferred in 1 hour, right, at the rate of 1 kilowatt or 1,000 watts, right? So if you have an appliance, okay, like an electric iron, for example, uses about 1,000 watts. Okay, so if you ran that iron for an hour, right, and if you ran it for 1 hour, then you would be talking about a kilowatt hour. And if your electric company charges 20 cents per kilowatt hour, then to run that iron for 1 hour would cost you 20 cents. Okay, now over the course of a month, maybe that's how long you run an iron. So it's going to cost you all about 20 cents. Now, that may or may not be our rate, but the point is that is how energy is measured in terms of electricity. Okay, now let's go back and let's talk about lamps for a little bit, light bulbs really, for a little bit. What's interesting is what wattage measures in a light bulb. Sorry. Right, 100 watt versus a 60 watt light bulb, right? This one is brighter, right? So it's how much power it's using, okay? And the funny thing is, though, especially with an incandescent light bulb, remember when I'm talking about an incandescent light bulb, right? I'm talking about this kind that you screw in, and it's got a little filament in here, okay? Most of that energy, 90% of that energy, is used up as heat, right? Incandescent light bulbs are very, very hot. Okay, now there is obviously some light also from this filament in here burning. Okay, that's the filament, but 90% of that energy is transferred to heat. Okay, now this is incandescent. Okay, now a CFL is a fluorescent type of light bulb. Okay, it's about uses about 26% of an incandescent. Okay, so for example, we're talking, if we want to compare a 100 watt incandescent light bulb, a CFL that produces the same light and heat would only use about 26 watts of power. Okay, so CFLs were something that started to take the place of incandescent because obviously they're a lot cheaper to run, right? And not only that, they produce a lot less heat. Most of their energy is not transferred to heat. Okay, it's a little bit warm to the touch, but not anything like an incandescent bulb. The problem with CFLs is they do have trace amounts of mercury. Okay, but here, and so that's only a problem really if you break it open. But here's the deal with mercury: those coal plants that produce the power to light up this incandescent bulb, they give off more mercury per incandescent bulb than this CFL gives off in mercury. So CFL is still better. And then in the last 5 years or so, we've had LEDs, which stands for light. I'm going to run out of room. Emitting, doesn't stand for that. Emitting diode. Remember, a diode is just a one-way switch, all right? So it's changing alternating current to direct current in that bulb. Okay, it's very, very small, all right? And these are maybe 6% of that 100 watt incandescent. Okay, you can touch these all you want. They lose hardly any heat. Their energy is not transferred to heat, and that's why more of their energy is for light, right? So they actually give off more light because their energy is not being transformed into heat. Okay, now LEDs are more expensive than CFLs, and CFLs are more expensive than incandescent. But over the long run, CFL is supposed to last about 7 times longer than an incandescent. That's not always the case, but LEDs are supposed to last 10 times longer than regular incandescent bulbs. So over the course of the life, of the bulb, your power consumption is very, very low. Your energy is very, very low with LEDs, but they do cost more up front. You probably are, looking at your phone. Your phone has a flashlight. It's just an LED, right? Any buttons that light up or that tell you that your computer is on, just an LED. Okay, they take very little power. So, just a little comparison of different bulbs that use different amount of power. Okay. All right, let's talk next about electric circuits. And we've used this term throughout this chapter, but I want to define it a little bit more, right? So a circuit is just any path that an electron can flow through, Okay, but remember, in order for it to be able to flow, it has to be a complete circuit. It has to be what we call a closed loop. Okay, and so I want to just kind of draw a picture of a circuit. So you have this. Okay, so this might be a battery, right? And it's going to have two little terminals. Okay, and one side's going to come out here. Okay, and this is a switch. Okay, and this is kind of hard to get, but when a switch is open, there's no flow. Okay, but when the switch closes, then we can have electrons, energy moving, right, from the negative to the positive. Okay, and so this might be a circuit. Now there's some inherent resistance in this circuit based on the wire, right? Maybe not very much so, but there's also resistance. Maybe we're just going to use light bulbs for the sake of our diagram here. We're going to put 3 light bulbs in here. Okay, now there's 2 ways to run a circuit. You can run a circuit in series, or you can run a circuit in parallel. This particular circuit is a circuit in series. Okay, and what that basically means is that there's one path for electricity to flow. Okay, it's going to flow around there and it's going to complete its circuit right here, and that's the only path. So what's the problem with that? Well, the problem with that is if one bulb breaks, then all of them, the circuit is now open and no electricity can flow, and so none of those bulbs can work, right? So but that's what a circuit in series looks like. Okay. Now the nice is a couple of other things about circuits in series. Okay. As the electrons are flowing through here, if this is a 6-volt battery, then the voltage across this lamp is 2 volts. The voltage across that lamp is 2 volts, and the voltage across that lamp is 2 volts. Okay, so the total voltage is split evenly among the devices that are on that circuit. Okay. All right. Couple of other things that you might want to pause as I say these, so you have time to write them down. The first one that I already said is that electric current can only flow in one direction, one path from the terminals of a battery or a generator or an electrical outlet, whatever the case, whatever the source is, doesn't matter. But in series, there's only one path from around the loop. Okay. All right. The second thing, all right, well, let me back up a little bit. So that means that the current going through each device that's on that circuit is the same. Okay. All right. The current is resisted by the first device, and then the second, and then the third. So the total resistance to the current is the sum of those individual devices along the path. Okay, now that's also a problem sometimes in that first lamp will probably be brighter, the second lamp will be a little bit dimmer, and the third lamp will be a little bit dimmer because the current, the resistance used up some of that current in that first lamp, and the voltage, remember, is the same, 2 volts across each one. And so it's going to get a little less current as it goes to each device. Okay. The current in a circuit is still equal to the voltage of the battery, the generator, whatever, divided by the total resistance. Okay, the total resistance of each device and in the wire itself. Okay. The voltage for each device is proportional to the resistance. Okay, so Ohm's law applies separately to each device. Okay. Ohm's law applies separately to each device. Okay. So when more energy is spent when a current passes through a large resistance than when the same current passes through a small resistance, right? So looking at just our basic I equals VR, the voltage is going to be the same. So if the resistance goes up, the current is going to go down depending on how big the device is, okay? The biggest disadvantage to a circuit in series is that if one device fails, they all fail, okay? So the counter to that, what somebody came up with, is what we call a circuit in parallel. Okay. And so we're going to go around, except that's not going to work. Let's try that again. Okay, so we're going to still have our switch. Okay. Actually, I want to draw that a little bit differently. Draw that a little taller. Okay, so we're still going to put 3 light bulbs on this. Okay, but the difference is we're going to have 3 paths. Well, and I just used that one up there. And each one is going to have its own switch. Okay, and so this one actually will be closed there. Okay, so our light bulbs here so now how many paths are there to complete the circuit? Well, now there's 3 paths. Okay, so I can have one go this way. Sorry, problems. I can have one go this way to complete the circuit, or I could have one go this way. So the first, I hope, obvious advantage to that is if one of those circuits goes out, the other 2 can still operate because there's another path for electricity to flow, for those electrons to give off their energy. Okay, that's the main benefit. You know, the biggest example that we have for this, obviously, are lights in your home, right? If something burns out, all of your circuitry should be wired in parallel, right? Power is flowing to each one, what we might say independently of the other. So if a light bulb goes out, then doesn't affect everything, every device on that circuit. Now, if a breaker blows or a fuse blows, that's something different we'll talk about in a minute. But if just that individual device goes out, the rest of the devices on that circuit can continue to operate. The best example, the most common example, is Christmas tree lights. Well, it used to be that if one Christmas tree light burned out or broke, the entire strand wouldn't work. But now they wire them in parallel so that a bulb can burn out and you can still have all the rest lit up. Okay, so that's an obvious benefit of a series in parallel. Okay, now a couple of things mathematically about the circuit in parallel. So the current divides among the parallel branches. So Ohm's law applies to each branch separately, okay, no matter how many devices are on it, okay? So the current divides among the branches, okay? So that means that the total current in the whole circuit has to equal the sum of the currents in the 3 branches, right? So if this one happens to be at 0.5 and this one's at 0.8 and this one's at 1, then that is the total total current for the circuit. And if I know that's a 6-volt battery, then I can calculate the resistance, so to speak, okay? All right. This is the crazy part, because of that voltage remaining constant and the sum of the currents being there, that as you increase the number of parallel branches, the overall resistance of the circuit is decreased, right? Because what are we doing? Well, we're adding current, and so resistance has to go down, right? Thinking about this, the voltage isn't going to change. So in order for the current to go up, resistance has to go down. Okay, so as you continue to add branches, parallel branches, the overall resistance is decreased. Okay, um, which kind of means that the overall resistance of the entire circuit is less than the resistance of any one branch. All right, so those are the kind of highlights of circuits in parallel. Okay, now we could have a situation though, we need to talk about this because it pertains to your house, so to speak, right? So if we have a circuit that kind of looks like this, okay, those are the two sides. This is power coming in from your power company, right? And we have a couple of things, and this is how you write a device in electrical circuit talk. Okay, and let's say this is a toaster and it draws 8 amps, and this is a heater, little electric heater that draws 10 amps, and then a lamp is 2 amps, right? And so this is one circuit. Okay, now that adds up to 20 amps. Okay, if you happen to have a fuse right here, right, a 20 amp fuse, then as soon as you go over that many amps, right, so if you add another circuit, a parallel circuit, and you add another device that draws amps, remember we have to add up all those amperages. If it goes above that, then you have overloaded the circuit. Okay, in earlier days before we had fuses and breakers, that could cause a fire, right? Because what happens, it would melt the wire that was carrying that current, right? And it could definitely cause a fire. But then what they did is they put a fuse in here. Okay, and there's lots of different types of fuse, but the basic theory and the way fuses work is that there's a little thin piece of metal in there that's allowing the circuit to remain closed, but it burns or melts sooner than your wires in your house do. And so when you get to over that 20 amps, it's designed to melt, okay, and burn. And what happens is that now that opens the circuit, and now electricity cannot flow through that circuit anymore, so it protects everything in here. Okay, now we don't really use fuses a whole lot in electricity anymore. We use breakers, which is using some magnetism and things, but it's the same idea, is that when the breaker notices that the amps, right, because you've added too many things, too many parallel paths, when the amps required goes up too high, then it shuts it down. Okay, it pops. That's what we call it, right? And we have in wires, right? You got the wire, and and then you got a plastic coating on the outside. Well, if you have two wires that are together and they rub against each other, or they get too hot and they melt that plastic, and then they touch each other at some point, then what happens is the path has just shortened, right? And that's why it's called a short circuit, because if that happens somewhere early, then the path for the electrons to return back might be real short because the wires have touched inadvertently, right? So that's why it's called a short circuit. All right. So electricity, a lot of fun, but also can be dangerous, but it's kind of fun to study and stuff. Well, we didn't get a chance to talk a little bit very much about how energy is supplied by the power company, but usually you might have what they call a 100 amp service. Okay, now 100 amps would fry anything in your house, right? So those breakers are designed to only allow a certain amount of amps through at a time. Okay, so sometimes you have fuses or breakers that might be 50 amp breakers, right? For like your oven or your dryer or something like that, because those require more power. But what do we know about the wire that supplies them? Well, they're going to be bigger, right? So that there's less resistance, so they don't get hot and burn up. Okay, so kind of just a quick rundown of electricity in your house. All right, so that's going to do it for us today. We have our power formula, we have our comparison of incandescent, CFL, and LED light bulbs, and then we have two different types of circuits. We have series, in which there's one path, and then we have parallel, which there could be multiple paths, and they each have their advantages and disadvantages. So that's it for chapter 23. Thanks.